So we are recording now. Good call. All right. So again, we haven't covered anything new. So there's nothing, we haven't missed anything yet. So just the balancing of equations is the first thing that we need to focus on. This flow chart, I will try and update or give you a better, what is more of my drawn version of this. I mean, this is okay, but again, this is more kind of stylized versus kind of how I usually do it up on the board. So for this next test, okay, mass and volume are both parts of things that we're doing for these experiments. Okay, we have molarity. We know what it is. We've introduced the term before. We know molecular weight. The only new thing here is the balanced equation. Okay, so we should be able to be comfortable with doing these conversions of mass to moles and volume to moles using these different terms. The balanced equation is the only new thing here. Okay, and yes, I will get these uploaded and get the videos posted here tomorrow. I didn't do the one from Monday, but I will get this one and the other one posted tomorrow as soon as I can. Okay, so what it comes down to for most of the stoichiometry that we're going to do, most of them can be done in about 3 steps. Okay, now this is not obviously if we start from something like moles, which is common. Sometimes we see a practice problem where it starts from moles and wants to just know moles of the product or know grams of the product. And so it's not quite 3 steps. Another way that this can be slightly longer than 3 steps is if they start with something like micrograms and you have to convert 2 grams before you can move on. And so it may introduce another step, but it doesn't functionally change the general order of these reactions. Okay, and again, the key thing here is that the molecular weight, the balanced equation, and the molecular weight here should not be your starting spot. Okay, in the problems, if you're given these pieces of information, these are probably not where you want to start. Okay. And all right, so this was an example here we talked about last night that is an example of a common reactant to product example. So this is most of what we see in most problems. Okay, we're told the amount of a starting reactant and we want to know how much product there is. Okay, this is actually asking what is the theoretical yield. Okay, so this number here at the end of this is the theoretical yield. How much can I get out of this reaction? How much can I get if I start with this amount of reactant? Now this one ignores the other one. Again, we talked about what was excess. So in this case, the ammonium sulfide is in excess, so we don't even worry about it. Okay. But when we get to, so the more difficult problems are when we have things like more than one reactant and we need to know what is the limiting reactant and what is the theoretical yield. So the way that I do this, again, there's a ratio way. The way that I do this is just to follow the same method for every problem. Okay, is so my 3 steps doesn't change. You're going, if it's mass, molecular weight, balanced equation, molecular weight, you have the same 3 steps. Whether you're doing that once through or twice through, you're still using the same methodology. Okay, so it doesn't change your process. And so hopefully that simplifies where you're going to make, or simplifies the problems and reduces down the mistakes that you can potentially make. Okay. All right, so this one, all right, so this one has both reactants. Okay, so this is one that we may have looked at last time, was where we have both reactants present, and it's just taking it through the process twice. molecular weight, balanced equation, molecular weight, molecular weight, balanced equation, molecular weight. Okay, so both of them are solved the same way. And the result here, okay, so let's look at the results. This again, this is where the results come from, is we want to compare whichever one is smallest. Okay, that's the outcome we want. All right, whichever one is smallest, that is your answer. Okay, because these reactions are reacting together until one of them runs out. And then obviously the other one could keep going, but it stopped over here because this first one ran out as it's making product. So you're looking at, we're making product, and then one of them stops and the other one can keep going. So so the reaction is going to stop at this first number. Okay, so at the 7 grams, that's where the reaction stops. Okay. Obviously, we can see this from a volume perspective. This is a separate reaction. So we talked about this one last time, where this is a reactant to reactant reaction. And so A and B are both reactants. So that's doesn't have to be reactant and product. It can be reactant and reactant. Okay. It can actually also be product going backwards to reactant. Okay. So this was again this was experiment coming up with the theoretical yield. And then from this one was the percent yield. Okay, so let's see where we're at here. All right, so I'll start to introduce this topic, and we'll look at a little bit of this. So this one here is where you're going to start to do some memorization. Okay, how do you know that both reactants? Okay, so if we look back, are you talking about the reactant one, the aqueous one, like this one? In this case, you would have an equation. You're going to have the equation, and so they're going to say that you have ammonium hydroxide, which is right here, and the acetic acid, which is right here, so that both of them are on this side of the reaction. So these are both reactants. Okay, so you're gonna focus over here on this side of the equation, and so you're always going to have this equation. Okay, so you'll always have an equation to work from. Okay, because you have to balance this. You can't. In the next section, we can write chemical equations. You'll learn how to write chemical equations, but for the most part, you're not going to come up with this as a balanced equation. You're going to be given the reaction. So you're going to know what particles you're dealing with. So if it's talking about these two things, you're talking about both of them are reactants. Okay? To answer your question? All right, so aqueous solutions. Okay, so this was going to be now, and this is really the sad part about not being able to go into the lab. This is my favorite lab that we didn't get to do, right? Because the lab was a total unknown. You had no idea what it is. All right, I gave you a little vial of clear liquid, and you had to tell me what was in there. And and so it really engages your critical thinking. You really got to think about, how do I come up with an answer? And then really to identify what was in this jar, what's in this flask. So, so as we deal with aqueous solutions, again, aqueous meaning that things are dissolved in water. Okay, so we're going to be looking at whether or not things are soluble. Okay, whether or not they dissolve in water, or whether or not they are insoluble, as in they don't dissolve in water. Okay, so when we see this AQ, again, that tells us that it dissolves in water versus something like silver chloride. Now, sodium chloride and silver chloride are both ionic compounds. Okay, right? So we know that water is polar. Okay, water is polar. So it dissolves polar compounds like ions. So ionic compounds should dissolve in water, right? But not all of these ionic compounds dissolve in water. Now, that's only partially true at this point because we're not putting a numerical value to the actual dissolving process. We're looking at it qualitatively of, does it dissolve or does it not? So technically, these things still do dissolve. Everything has some amount of solubility, but for our purposes, it's going to be a holistic thing. Is it going to dissolve or is it not? We don't have any numbers to go on here. Okay. So we want to know, how do I know what salt is going to dissolve, right? If I give you an ionic compound, how are you going to know if it dissolves or not? Okay. So I'm going to skip this is just some definitional stuff that honestly, these are mostly kind of the same in how these work. So this is just a picture here of like how dissolving works. Is it, you have the ionic compound, the salt, right? And the polar water is attracted to the ions, and it's more strongly attracted to the ions than the ions are holding themselves together. Okay, so as soon as it gets attracted, then water kind of scoops this ion out, and so you'll see the water is positioned differently. So here the hydrogens are at the bottom because they're attracted to the negative, versus the positive is where the electrons were at the top, and so they're attracted to the top part of the molecule. All right, and so water gets into the crevice and kind of peels one off, and then from there, like, it begins to break down the crystalline structure. All right, so some of our first things that are important as far as definitions are electrolytes. Now, most people have heard of the term electrolyte, and it is a solution that conducts electricity when it has ions dissolved in water. Okay, when it has ions dissolved, it can be electrically conductive. Okay, so if it doesn't conduct electricity, then it is technically not an electrolyte. And so this is where we come across electrolyte and things like, we get Gatorade and things like that, where they talk about recharging your electrolytes. And it's really just that there's things like sodium and potassium in there. But regular water has plenty of ions in it. You don't technically need, Gatorade doesn't, as far as I'm aware, doesn't, produce or provide. I mean, your body absorbs what it needs and then disposes of the rest. So if you can get all the ions you need from water, and it's not like it absorbs into your body faster by being Gatorade, so it's the same absorption rate and everything like that. So whether you drink water or drink Gatorade, you're still recharging your electrolytes, but at least without the Gatorade, you're probably not getting the diabetes to go with it, okay? Because those drinks are mostly just sugar, and if you can just get away with just drinking water, you really don't need the other thing. So again, those things are mostly marketing gimmicks of getting, selling you, sugary beverages essentially, right? So a strong electrolyte means that it dissolves 100% in solution, okay? So you're gonna see this same definition here of strong and weak later when we talk about acids, okay? But we're just talking about that the ion separates 100% into its ions, okay? And there'll be some ways that we can differentiate what is strong versus what is weak, okay? But we're looking at things that are going to dissolve in water, right? Or create ions in water. Now, there are things that obviously that dissolve in water. Water is a very good solvent. So non-electrolytes also are dissolve in water, things like sugar. Okay, sugar dissolves in water, but sugar is an organic molecule. It is not an ion. It does not make ions in solutions. So sugar water is not an electrolyte. It still dissolves just fine, right? But it doesn't conduct electricity because there's no ions present, and so it is considered a non-electrolyte. The same things of like ionization and stuff like that, these are, less, I kind of tend to use these same kind of words of, dissolving and ionization as similar. And so here, but it introduces the same kind of issue where acids are really, that's really what they're doing, is separating in solution. And so when you do that, when they separate in solution, you get that donation process, right? That we talked about that in the nomenclature section, where an acid is defined as an acid because it donates a proton. Okay, so in this donation process, it is actually donating it to water, right? That's what the aqueous portion was, is that HCl was donating it to water, but in the process, it also separates 100%. Okay, and so we could classify acids as strong acids versus weak acids, because some acids are going to separate 100%, and some are going to donate a little bit, but then it comes back. And so there's always some percentage of it that is in the original like acid form, and so we can have weak acids, right? For acids and bases, this does not mean anything about how dangerous they are. It does not mean anything about how corrosive they are, okay? HF, okay, hydrofluoric acid, is a weak acid, all right? But it is extremely dangerous. It is incredibly corrosive. Most chemists don't really want to deal with it if we can avoid it. It's kind of one of these ones where it not only, I mean, it's just as corrosive as HCl is. So hydrochloric acid is right below hydrofluoric acid. So the two acids, but hydrochloric acid is a strong acid. So hydrochloric is a strong acid, hydrofluoric is a weak acid. They're both incredibly corrosive, but I'd much rather work with HCl than HF. The other things of like, HF, you also can, will cause your bones to become brittle. So even after you get it on you, it's not just about the chemical burn. It's also what it will do to your internal bone structure too, being exposed to it. So it does not mean that it's not dangerous. Okay, so strong and weak is not about how dangerous it is. It is exclusively about how much do the ions separate. Okay. So this is my example here, looking at salt water is obviously electrically conductive versus sugar water does not. All right. All right. So if we're looking at things where we're classifying things as strong electrolytes, weak electrolytes, or non-electrolytes. Okay. So this is a relatively good test kind of question, is just being able to identify the different components. Okay. Calcium chloride. Well, we don't know so much enough to, at this point, whether or not it's a strong electrolyte or not. We know it's an ion, so it's likely that it's going to be at least an electrolyte, right? C6H12O6, sugar, okay, is a non-electrolyte. We have nitrous acid, which is identified as a weak acid, which also makes it a weak electrolyte, okay? Weak acid, weak electrolyte. Strong acid, strong electrolyte. Okay, those definitions are pretty much synonymous for the most part. Okay, so ammonia is a weak base, so therefore it is also a weak electrolyte. Okay, potassium hydroxide, again, we don't really know, but one thing we can say for sure is it is ionic. Okay, we have potassium and hydroxide. Again, those polyatomic ions are still going to be important this time, right? Potassium and hydroxide is an ionic compound, so at least we're fairly certain that it's not a non-electrolyte. And then HBr is a strong acid, so therefore it is also a strong electrolyte. Okay, and so whether or not it's a strong electrolyte, we don't have enough information yet in order to make that call, but you'll have some information here in a few minutes as I get to the slide, which I may do right after the break here. All right. All right. So I'll leave it on this slide here as we go to break. So determining whether or not something will dissolve. So this goes back to that question of sodium chloride and silver chloride. So we have both. They're both ionic compounds. The question is, how do we know which one is going to dissolve? Now, I showed you already that silver chloride doesn't dissolve, but just from looking at the structure, we wouldn't know. We can't tell that from just looking at them. They're both, salts of chloride. So presumably we might think that they both would be soluble. All right. And so this is the first slide here. And so this is where I'm going to leave it here. And this is the most important of the slides on the solubility. I call this my rule number 1. Okay. So rule number 1 is the most important rule of all of the solubility rules. Okay. These ions, if you see them in the solution, they are always soluble. Okay. They do not form solids. Okay. So if they don't form solids, that you can eliminate out possibilities, because a lot of the questions are going to be things like which these will dissolve. Well, any compound that has these in it is going to dissolve. If the question is which ones don't dissolve, if it has any of these in it, that's not the answer. Okay, so these are always going to be soluble. They will always dissolve. They will they're not going to be a solid. You're not going to get sodium chloride in a solution that's solid. Okay, it's automatically going to dissolve and be aqueous. Okay, so these ions here are the most important ones for you to have memorized. You have to memorize these. Okay, these are the most important ones to have memorized, and we'll talk more about why a little bit later. Okay, all right. So let's take a few-minute break here. I need to go get a refill, and then we can reconvene. We'll finish this section, and then, like I said, we'll probably end up a little early. Again, we don't have to push too hard because we do have plenty of time to get through some of this. All right. So if you have questions, think of your questions, and you can post them in the chat, and then I'll get to your questions as soon as I get back. But we'll take 5. All right. And let me pause our. All right. So we have now the expanded list here. So this is going to be, it's a couple slides. So the first one is the most important ones. All right. And now we go to, so these ones, so the first ones were always soluble. Okay. So these are always soluble no matter what. Next, we have things like chloride, bromide, and iodide, and sulfate. So these are generally soluble, except these ones have exceptions. So when they're paired with things like silver, mercury, and lead, they are insoluble. They form solids. So that's why we saw the silver chloride was a solid when sodium chloride wasn't. Okay, so sodium chloride was going to be aqueous, and silver chloride is going to be a solid. So when it mixes with these, so when these ions mix with these, then they make solids instead, right? And so you have to know what are the exceptions to the rule, okay? So for the sulfate, again, it's generally soluble except with silver, calcium, strontium, barium, and lead, okay? All right, so then we have the generally insoluble compounds. things like hydroxide, sulfur, carbonate, and phosphate, these are generally going to be insoluble. So they're going to want to form solids. Okay, so if they're there, they are more likely to be a solid rather than being soluble. Now again, here they have exceptions, and so with the exceptions, they are soluble. And so you'll notice here that the exceptions are the rule number 1 ions: lithium, sodium, potassium, ammonium are the first rule ions. So here, when these ions are present, rule number 1 is the dominant rule. Okay, so it doesn't matter what hydroxide wants; these ions are more important. Okay, now there's some slight solubility with calcium, strontium, and barium. For test questions and things, I would just consider these to be soluble. Okay, I wouldn't. If we were in the lab, you would see some slight difference. These tend to be where they look kind of cloudy when you pour them. So if you had like a barium hydroxide solution, it can be kind of cloudy, where you don't really see a solid per se, but you can't really tell, like if there's not like solid present, because it's mostly suspended. And so again, the sulfurs or the sulfides are generally insoluble, except with the rule number 1 ions: calcium, strontium, and barium. Carbonates and phosphates are generally insoluble, except for the rule number 1 ions. Okay, so these are the things you kind of need to have memorized. Okay, so you've got time. Okay, so these are things that you would want to have memorized for test questions. Okay, all right. So one of the first kinds of questions that we have with using the solubility rules are: will it dissolve in water or will it not? So if we take this ion and I put it in water, what's going to happen? Okay, so this is where, if you identify those first ions, those rule number 1 ions, things like sodium. Okay, sodium was a rule number 1 ion. If sodium's present, it's soluble. Okay, so you don't even need to know anything about the phosphate. Okay, the magnesium sulfate. So again, this is where you kind of got to go back to the solubility rules and having things memorized. So there were sulfates, and so the question really is do you have memorized, like, was magnesium one of the exceptions or not? There were exceptions with sulfate. Silver and the sulfurs are generally insoluble, so the likelihood is that it's going to be insoluble. Okay, and so the top 2, we're not doing any reactions. This is just a salt. If I take this salt and I put it in water, what's going to happen? Okay, so that's the first kind of question. Now, different ways that these kinds of questions are phrased is things like, given these 3 salts, how many are soluble, right? Or given these salts, how many are insoluble? Okay, so it may not be simply, is this going to dissolve in water or not? It could be out of a cluster of salts, and you have to figure out how many are going to be soluble or how many are going to be insoluble. Okay, so that's kind of the other way that this is often phrased. All right, I'll skip we'll do that one for next time. All right, so the real bulk of these kinds of questions where you want to focus with the solubility rules are precipitation reactions. Okay, what I will probably do is give you a this might be one where I could give you stuff to do as a homework thing, or not. Again, it's we can work it out later. Is to be able to write these 3 reactions. Okay, there's a molecular equation, a total ionic equation, and a net ionic equation. There's also determining what are the spectator ions. So these are all different questions that you might find. Is writing the molecular equation, which again, now that I've done kind of a take-home component of the test, that's obviously a likely way of doing it again, I could. I guess it's just a matter of how easy it is to make the exam with all of these things, because again, the reactions they're not too hard to put in there as you know, as answers. So it's just more of a lot of the subscripts and stuff. But I mean, we can do a take-home portion again for the exam, which again I may kick around, but we'll see. But writing the molecular equation, writing the total ionic equation, writing the net ionic equation, and then what are the spectator ions? So that's 4 different kinds of questions that we could get from this one section, okay? All right, so when we do precipitation reactions, all right, all of these reactions, okay, are double replacement, okay, which means that when you take, say, lead nitrate and potassium iodide here, the double replacement means they are going to swap partners, okay? The potassium is the cation, the lead is the cation. They're going to just swap partners and double replace who they were with, okay? So they're just going to swap their dance partners. And so as a product, now I get lead iodide and potassium nitrate, okay? So on a test question, you might not have, the products might be missing, okay? The products might not be given in the problem, where you have to write what are the products of the reaction, okay? But the products are always generated the same way. They are all double replacement reactions. So if I give you the reactants, you should theoretically be able to swap the partners and make the compounds that they make, okay, as products. Now, the key for making this is when you have these ions is that they're both soluble to start with. So potassium iodide is soluble and lead nitrate is soluble. The question is, what happens after they mix? Because these are just ions floating around in solution, right? So what you have is ions floating around in one solution and ions floating around in another solution. And as they go together, you know, obviously A and B were already soluble, C and D were already soluble, but now you have the interactions of A and C and A and D, B and C and B and D, or not really, because I mean, the positive ion A to D and B and C is the new reaction. So the question is, what happens when they make, you know, when something happens? You know, is something going to make a solid or is it not? Okay. All right. So here we go. So here's our first example of what this will look like. Okay. You have sodium phosphate and calcium chloride. We need to write the equation for what's going to happen. Right. So the sodium is going to swap partners with the calcium. Okay. So the sodium is going to swap with the calcium, and so we get sodium chloride and calcium phosphate. But again, for your nomenclature stuff, you got to put the right molecule together, right? So when you take the calcium and the phosphate, you've got to put them together properly, all right? Nothing is going to change charge, okay? That's an important statement. Nothing is going to change charge as you do this. The calcium is always going to be +2 because that's what its oxidation state always was, right? But if we look down here at the nickel, okay, nickel in this case is +2. So when it remakes over here, it is still +2, okay? It does not change the charge in this process, okay? If it changed charge, you wouldn't be able to come up with the product. You wouldn't know what the product was, okay? It doesn't change charge. So whatever it is as a reactant, it is going to stay that as a product as far as its charge. We just have to remake the proper molecule at the end, Okay. Now I put X's in here because that's really our next step is what happens when these get made? Does this become a solid or does it stay aqueous? Or maybe it makes a gas or a liquid. That can actually happen. We'll cover that in one of the other reactions. Okay. But from our solubility rules, okay, sodium, one of our rule number 1 ions, so it's going to be aqueous. Calcium phosphate, well, phosphates were generally insoluble, and calcium was not one of the exceptions. So the phosphates are generally insoluble, so they are going to form a solid and clump up and fall out of solution. Okay. Potassium carbonate, potassium is a rule number 1 ion, so the potassium is still going to be aqueous. But nickel and carbonate are in the carbonate, so carbonates were generally insoluble, so they're going to make a solid product. Okay, and so we have to fill in this and then also balance the equation. Okay, so there's a lot to do in writing a good molecular equation. It's forming the right molecule, balancing the equation, and then filling in the proper phase of what happens. Okay. So this is writing the molecular equation. All right. We'll look at the ionic one here as our last one here. Okay. So if we have the molecular equation, okay, the second equation that we want to be able to do is the ionic equation, which is simply the same equation, just we're going to separate everything that's aqueous. Okay. Separate everything that's aqueous into their ions. You don't separate solids, liquids, or gases in this step. Okay, so what you're going to see here is here's silver nitrate. It gets separated into silver and nitrate. Sodium chloride is aqueous, so it gets separated into sodium and chloride. The silver chloride is a solid, so it gets written as silver chloride. The sodium nitrate is aqueous, so it gets separated into sodium and nitrate. Okay, and this is the total ionic equation. Okay, this is what's called the ionic equation or total ionic equation, where we separate everything. Okay, separate everything into their ions. The only things that don't separate are solids, liquids, and gases. Okay. Let's see, I don't think there's anything else to. All right, so we'll stop here with this. All right, so that's it. We'll pick this up on Monday, presumably after I deal with the last one person that's got some slight thing. Then we can look at the test on Monday. If you want to go over it again, I have the key for the actual test. We looked at the sample one that I had put together, but we can actually go over the real test if you want. Also on Monday, I will have probably the lab items posted for what I want to do for the lab. Like I said, I was going to focus on conclusion. So we'll probably talk about some conclusion writing on Monday, and then I'll have those assignments for you to do to make up those for those labs that we missed. Okay. That's about all I can think of. Like I said, you should be thinking about your topic. Okay, so be thinking about your research paper topic. That'll be coming up. I'll probably post that along with the research paper assignment. Okay, so you should be thinking about your topic. If you need help, you want suggestions or ideas, you can email me. We can talk. We can talk in the Zoom group meeting during the next class or something like that. If you're thinking about stuff, like I said, I also log in early. So if you want to log in early and talk about or after I'm done here, we can talk about stuff too, like before or after class, we can talk about research paper ideas if you're kicking something around or you're not sure what to do. Obviously, things like, coronavirus might be, an interesting topic. I'm sure there will be at least, someone who wants to do that. Again, I am fluent in biology and chemistry, physics, geology, variety of other sciences. So whatever topic you want to write on is fine. So again, it does not have to be exclusively about chemistry, but, has to be a science topic, and something that you can write a decent topic on for a couple of pages. All right. So if there's no questions, I will hang around if anybody has questions. Otherwise, I will